Alright, so for this question, h index, given an array, and we want to find a number between 0 and 1000 such that, let's call it h, such that the number of elements greater than or equal to h in the array is equal to h. So for example, if we take this array, and then we sort it, so we get 0, 1, 3, 5, 6. And we choose 3 as our h. So that's the number between 0 and 1000. And we see how many elements greater than or equal to 3. Well, 3. So that will be the answer, right? And we want to choose the maximum value of h that satisfies this condition. So if you choose 5, for example, how many items greater than 5? 2. Well, it doesn't really match 5, so that can't be that. And because we know that 2, number of items greater than 5 is 2, we know that the answer must be before 5, before that number 5. It has to be less than 5. And if we choose 1, for example, number of items greater than 1, 3, 4. And that number, so the number of elements greater than 1 is 4, which is greater than our h, which is 1, which means the answer must be greater than 1. So we can actually use binary search to find the answer. And that's the first approach I'm going to go through. So that kind of relies on me sorting the array. Sort citations.end. So I've sorted the array, and to find how many elements greater than a particular number, we could use a little trick called lower bound. So lower bound basically does a binary search for you. It finds the first number greater than or equal to your target number that you're searching for within the array, and it returns an iterator to that, so like a pointer to that element. So let's do that. So citations.sort, citations.end. Let's say I'm searching for 3. So that returns an iterator. And to find how many elements greater than or equal to 3, it will just be the distance to the end of the array. So the end of the array is going to be citations.end, and then minus iterator. That will give me the distance, because this is vector. So vector is contiguous in memory, so I could just say, where is the end? Where is the item I found? Distance between those would be the number of elements. So that will give. So that's how you can do. Let's just begin. Do binary search in a very easy way. Why did I say sort here? Begin. Let's use this example. So copy that. See what we get. Okay, 3. Alright, so let's use this approach. We actually need an outer binary search. So the binary search, we could go through the range 0 to 1000 and maintain some invariance until we find the answer. So we can do something like int low is equal to 0. So we want the low to be less than or equal to the answer. That's the invariant I choose, and 1001 to be the high. So I want that to be high, strictly greater than the answer. So I don't want that to be equal to the answer at any point, because the answer could be 1000. I don't want it to be 1000, so I set it to 1001. And then to do the binary search, like always, we just do low minus high minus 1. So while they're not next to each other, keep looping. Calculate the middle value. So mid would be equal to low plus high divided by 2. And then we have our if statement to check the lower bound. So the lower bound is this. We're going to get the distance. So we're treating mid as the h value, as our h index. And we see if mid is a suitable h value. So if the distance, so if citations.end minus the iterator, so if the number of elements greater than mid, greater than or equal to mid, is greater than or equal to mid itself, then I know that the answer would be greater than mid. Greater than or equal to mid. So I need to say low is equal to mid, right? Else high is equal to mid, right? And then all I have to do is return low. Okay, so that was my first solution, but there is a faster solution apparently they haven't done yet. I was hoping I could do it now. So let's try that out. Okay, it's kind of slow. So let's see how we can do this a little bit faster. Well, what we can do to not sort it, so the time complexity here is that this part here is log n squared. That's pretty fast. Definitely better than n log n. So this is definitely faster than this, which is n log n. So if you can get rid of the sorting and do something in linear time instead, then we're sweet. So how do we do something in how do we get rid of sorting? We can, because we see that the number of citations is quite low. We can just keep an array of size 1001. So int, let's say count 1001. What's neat is that if you declare it as a global variable like this, all the items is initialized to 0. Let's actually get rid of this. And then we just count all the we can count all the items here. So if for 3, we increment count of 3 by 1, and so on. So what happens when you do that though? How does that help us find how many items greater than or equal to some certain number? So you could do like suffix sums. Because if you go through from the top to, from the right end to the left end, we could just accumulate the number of the counts as we go along. And at some point when we find that the counts, that the accumulated sum is equal to the current h value, then we return that answer. So let's see if that works actually. So you have 0, 1, 3, 5, 6, and so that means we have 6 numbers in an array initially. 1, 2, 3, 4, 5, 6. So this will be our count, and then we go through each of these and we increment the 1. So this will be 1. This will be 1. This is be 1, 1, 1. And we loop through from the right to left, and then we count. 0, 1, 2, 0, 1, 2, 3, 4, 5. Okay, I've done the counting wrong. I missed 4. So this is 0, 1, 2, 3, 4, 5. So it's 0, 1, 2, 3. It's all good. This should be 0. This is for 5, and this is for 6. Got a little bit confused there. Okay. So we check, could the h index, we set h index to be equal to 6 and say, what's the count so far? 1. Does 6 match 1? No. So keep going down. The total sum is 2, and the h index is 5, doesn't work. So we keep going. It's 4, it's 2. And then we get down to here, there's 3 and 3. Okay, cool. Okay, but what if this is 2? Then we'll be like, oh, they don't match. That's a problem. So we can say that's 1, 2, 4. And we see that the count is actually greater than this. The first time it's greater than or equal to the index, so that means that is the answer. So yeah, so I just figured out that the first time it's greater than or equal to the index, then we should return that index. So let's try it and do that approach. So we're doing 4 for each item. So for each, just do a range loop and say auto C in citations. The count of C, increment it by 1. Okay, and then go through up to 1,000. I greater than or equal to 0, minus I. For each of these indexes, while if, so I'm going to accumulate count, sum is equal to 0. Sum plus equals to the count at 1001. Count at I, actually. Say if the sum is greater than or equal to I itself, then return I. And then here we just return 0. I don't think we'll get up to this point though. Alright, so that's 3. That also works. Let me think. You can have 0. Right, that seems to work. Let's give that a go. Awesome. Alright, so that's the fast solution. But less space isn't as good, of course.